In the early 20th century, Albert Einstein became a star overnight by publishing two groundbreaking papers, including the theory of relativity. Unlike most rapidly rising stars who fade away, Einstein continued to achieve remarkable results in everything he touched, gaining attention in the scientific community and eventually being recognized as one of the greatest geniuses in human history. The reason his achievements are particularly noteworthy is that he ventured into fields that scientists had not even dared to approach until then. He created tools to unravel the mysteries of the universe, which had remained an unknown territory for millions of years. Einstein began to explore something universal that exists everywhere, from our surroundings to the edge of the universe, in order to tell the story of the cosmos. Eventually, he ended the centuries-long heated debate in the scientific community about light. Given that it was a debate unresolved for hundreds of years, the result was quite astonishing. Light could be both a particle and a wave. This was a story that overturned the established common sense of the scientific community, making it hard to believe. But following his logic and narrative, one couldn't help but accept it as a fact. Scientists, having realized such an astonishing fact, began to delve further into studying light, which they had not been able to touch until then. Among them, inspired by this, Dr. Davison and Dr. Germer succeeded in uncovering even more surprising facts through Thomas Young's double-slit experiment, which had revealed the wave nature of light. That is, not only light but also matter has wave properties. The electron, which we had believed to be a particle, or had never thought of as a wave, actually possessed wave properties. This was a massive shock to the scientific community. Scientists then all rushed to explain this seemingly absurd phenomenon. Among them, Heisenberg and Schrödinger each succeeded in describing this phenomenon in their own ways. They expressed the states of matter as particles and waves through matrix mechanics and wave equations, respectively. At this point, an unexpected problem emerged. Heisenberg's matrix mechanics was a new form of mathematics that had not existed before. As a result, it did not gain much trust from classical physicists who were accustomed to the existing mathematical framework. Among those skeptics was none other than Einstein himself. Einstein could not accept Heisenberg's matrix mechanics nor the Copenhagen interpretation of the phenomenon that Heisenberg and his mentor Bohr proposed. Einstein, who could not accept this, dedicated almost his entire life to fiercely attacking their ideas. Today, we will explore the scientific topic of why Einstein denied quantum mechanics from the comfort of our room. Let's get started right now. In 1923, at the young age of 23, Heisenberg obtained his doctorate and began collaborative research with Max Born, one of the leading mathematicians and physicists of the time. During this period, he was also summoned by his mentor Bohr to Copenhagen, where he endeavored to formulate Bohr's atomic model into equations. In 1925, upon returning to Göttingen, Heisenberg suffered from a severe pollen allergy and took a 2-week convalescence. During his stay on this island, Heisenberg worked on formulating Bohr's atomic model into equations. He had his own principles in this endeavor. Since the exact position and momentum of an electron could not be precisely observed, he excluded them. Instead, he focused on the wavelength and intensity of the light emitted by atoms, which could be accurately observed through experiments. He wanted to create a theory based solely on these observable values. Despite the seemingly nonsensical phenomena shown by quantum theory, he believed that the law of conservation of energy would not be violated. As a result of his thoughts, he ended up with a series of incomprehensible numbers. What he discovered could be described as a giant table. Using this table, he could calculate the intensity of light emitted when an electron transitioned from one orbit to another, confirming that the law of conservation of energy held true in the process. The problem was that the calculations using this table exhibited bizarre properties. Changing the order of multiplication led to entirely different results. For instance, multiplying 1 by 2 should yield the same result as multiplying 2 by 1. But in his calculations, 1 times 2 resulted in 2, whereas 2 times 1 resulted in -2. After his convalescence, Heisenberg rushed back to Göttingen to discuss this issue with Max Born. Initially, Born also struggled to understand the peculiar mathematical rules in Heisenberg's results. However, he soon realized that what Heisenberg had discovered was matrix multiplication. A matrix is an array of numbers arranged in a rectangular form. The order of the numbers is crucial because the sequence of calculations changes depending on how the numbers are arranged. Matrix mechanics, which emerged from this discovery, not only perfectly expressed Bohr's atomic model in equations when considering electrons as particles, but also provided a new means of interpreting various phenomena. While most scientists welcomed this new interpretative tool, not everyone was enthusiastic about Heisenberg's discovery. The introduction of a completely new set of mathematical and calculation rules, as opposed to traditional methods, was enough to provoke resistance from classical physicists who were accustomed to conventional calculations. Among them was Albert Einstein, a leading figure in classical mechanics. However, if someone could describe quantum theory using traditional methods, it would likely gain support from classical physicists who were unfamiliar with and opposed to the new approach. The person who achieved this was the Austrian scholar Erwin Schrödinger. At that time, the concept of matter waves, which proposed that matter could exhibit both particle and wave properties, was emerging. Inspired by this, Schrödinger set out to find a new wave equation to explain the spectrum of the hydrogen atom. Contrary to Heisenberg, who focused on the particle nature of electrons to develop matrix mechanics, Schrödinger concentrated on the wave nature of electrons and sought to express it mathematically. Finally, in the Christmas of 1925, Schrödinger formulated his famous wave equation. His equation took the form of a differential equation, a type of equation familiar to physicists for many years. Thus, it was accepted without much resistance. The problem, however, was that even Schrödinger himself could not interpret what his equation meant. In classical mechanics, which Schrödinger and most physicists had studied, inserting initial conditions into Newton's equations of motion yielded a single solution, allowing for the prediction of future events. For example, if one starts at point A and travels at 3 kilometers per hour for 3 hours, it is possible to predict that one will be 9 kilometers away from point A after 3 hours, and this prediction would be accurate. Although solving for more complex initial conditions might be challenging, it was only due to a lack of mathematical ability, not a flaw in the equations themselves. In other words, as long as the exact initial conditions were known, the equation with these conditions would yield a single solution, accurately predicting future events. However, Schrödinger's equation was different. Solving his equation with initial conditions did not yield a single solution, but multiple solutions. In other words, if a wave started at point A, instead of arriving at point B as expected, the Schrödinger equation suggested it could be at point B, C, or even D. The wave function was a highly abstract mathematical construct and, by itself, did not have physical meaning. However, at this point, a man enters the scene, the great mathematician and physicist who greatly helped Heisenberg complete matrix mechanics, Max Born. Max Born felt that something was lacking when he saw Schrödinger's equation. As it was an equation based on the properties of waves, it seemed to have some physical significance. After pondering for several days, Born finally understood the meaning of this equation. He took the absolute value of Schrödinger's wave equation, squared it, and produced a graph he had seen somewhere before. This represented the probability density of the particle's existence, meaning the probability of finding a particle at a specific location. If there is one electron in a box, the electron has wave-like properties and is spread out over a certain range. The electron could be at the corner of the box, in the middle, or in an uncertain space. Everything was just a probability. However, Schrödinger himself could not accept this result. For classical mechanics, scholars who always sought precise values, the idea that an electron's location could only be determined by probability was incomprehensible. Thus, Schrödinger could not accept that his paper had resulted in mere probabilities. And to criticize such absurd claims, he conducted a thought experiment. This is the famous Schrödinger's cat. Max Born, who created the probability density function by transforming Schrödinger's wave equation to determine where the electron might be. However, Schrödinger himself was not pleased with Born's interpretation of his equation. In the world of classical mechanics, where all values are exact, the idea that a value could exist probabilistically was almost like gambling. Thus, Schrödinger, unable to understand Born, even sent him a letter saying, "I truly respect you, but I find it difficult to respect your views. Aren't you worried about the judgment of history? Are you really sure that humanity will succumb to your foolish judgment?" This showed that Schrödinger did not respect Born's research at all. Moreover, in 1926, another great physicist of the time. Einstein, who also could not accept Born's theory, sent Born a letter. One of the sentences from that letter has been passed down to this day as a catchphrase symbolizing quantum mechanics. Quantum mechanics is certainly impressive, but my inner voice tells me that it is not yet the real thing. The theory says a lot, but it does not bring us closer to the fundamental secret. I am convinced that he does not play dice. In other words, Einstein believed that the world was not and should not be based on probability. In 1935, finally, Schrödinger conducted a thought experiment to criticize the increasingly influential quantum mechanics. First, he prepared a box that could never be looked into. He placed a cat and a bottle of poison inside the completely sealed and opaque box. He also added a device connected to a hammer to detect radiation, along with a uranium particle that has a 50% chance of decaying and emitting alpha particles in 1 hour. If the uranium particle decays after an hour, the radiation it emits will be detected by the device, causing the hammer to break the bottle of poison. According to common sense, the cat that ingested the poison should be dead. However, according to the Copenhagen interpretation of quantum mechanics, the state of the cat cannot be determined until the box is opened. In other words, until we open the box and observe the cat is either dead or alive, the cat inside the box is both alive and dead simultaneously. If we never open the box, the state of the cat will never be determined. Such a notion is hard to accept, even for us. This was also the case for Schrödinger, who proposed the thought experiment. The idea that the cat is both alive and dead simultaneously is logically difficult to understand. Let's assume such a phenomenon occurs in the microscopic world. If superposition occurs in the microscopic world, it should also occur in the macroscopic world, which is made up of the microscopic world. A cat is a macroscopic entity made up of trillions of atoms. But have we ever seen a cat that is both alive and dead simultaneously? Schrödinger argued that because superposition cannot occur in the macroscopic world, it cannot occur in the microscopic world either. This seemingly plausible argument seemed to undermine the Copenhagen interpretation. However, the Copenhagen school was not dismayed, they even appreciated it. The thought experiment that Schrödinger devised to point out the flaws in the Copenhagen interpretation ended up showcasing the essence of quantum mechanics. The explanation that an electron can exist probabilistically was too unfamiliar for people hearing about quantum mechanics for the first time. The idea that matter could also be a wave was already new, and now the existence of matter itself was probabilistic, which was hard to understand. But Schrödinger's cat thought experiment made it easier for people to understand what quantum mechanics was. Moreover, by mentioning the microscopic and macroscopic worlds, Schrödinger was the first to propose the connection between the two. Thus, intending to criticize quantum mechanics, Schrödinger inadvertently filled in some gaps. However, there was still a significant challenge for quantum mechanics, the most formidable figure who had remained silent until now, Einstein. Einstein believed that all the secrets of this world would be mathematically solved perfectly. He also thought that this seemingly complex world was made up of just one equation. However, the fact that he had to rely on probability to explain the very small particles that are the basis of this world was enough to make Einstein furious. Fortunately, the stage was set for classical mechanics, which Einstein had believed and researched to fight against the newly emerging quantum mechanics that broke the framework of classical mechanics. This stage was the Fifth Solvay Conference held in October 1927. The Solvay Conference, which started in 1911, was the most prestigious scientific conference in the world. It was a place to discuss really important, unresolved problems in the scientific community at the time, or to come up with some ideas. Coincidentally, the topic of the Fifth Solvay Conference was electrons and photons. 29 scientists were invited here, and among them were 17 Nobel Prize winners, including Einstein. It was called a gathering that would never happen again in human history. In such a place, Einstein and the Copenhagen school began to fight over the existence of quantum mechanics. First, Niels Bohr stepped up to explain the great theory created by the Copenhagen school, quantum mechanics. Quantum mechanics was such a difficult and esoteric discipline that they wouldn't expect everyone to understand it all at once. The problem was that Bohr was too poor at speaking. Some scientists who listened to Bohr's presentation said they were on the verge of rejecting quantum mechanics because they couldn't understand what he was saying. Eventually, Bohr decided to change his strategy. If he couldn't persuade many people at once, he decided to make them understand one by one. So Bohr explained quantum mechanics to each person for 5 days until their ears were almost bleeding. The scholars who listened to Bohr's explanation had no choice but to reluctantly accept quantum mechanics. On the third day of the Solvay conference, Bohr finally thought that quantum mechanics was being recognized by people. However, there was someone they were overlooking, and that was Einstein. For some reason, Einstein did not raise any objections throughout the Solvay conference and listened to their stories quietly. It seemed as if he had finally accepted quantum mechanics after listening to Bohr's explanation. But when Bohr said that quantum mechanics was a perfect theory, Einstein couldn't hold back any longer. He couldn't accept that phenomena were explained merely by probability without being able to measure the exact position and momentum of particles. To Einstein, the inability to measure these precisely sounded like an excuse. He saw it as a problem that would be solved once the observation equipment developed. So, Einstein began to attack the foundation of quantum mechanics, the principle of uncertainty, with a thought experiment. He brought an interesting object called a modified double slit. In the first slit, a tiny hole was made in the shape of a rhombus, and behind it, a slit with 2 holes that we know was placed. When electrons were fired at the first slit, since the electron had the properties of a particle, if the electron hit the bottom of the hole, it would bounce up, and the slit would move down. Conversely, if the electron hit the top of the hole, it would bounce down, and the slit would move up. And the electrons that passed through the first slit would arrive at the next slit and create an interference pattern. At this time, through the movement of the first slit, the particle nature of the electron could be known. At the same time, through the interference pattern, the wave nature of the electron could also be known. In other words, he claimed that the principle of uncertainty, which states that if you observe the electron, it behaves like a particle, and if you don't, it behaves like a wave, was incorrect. That observation was meaningless, and thus the principle of uncertainty was wrong. The scholars at the conference at the time thought that quantum mechanics was about to collapse with such a sharp question. However, Bohr did not panic and directly refuted Einstein's thought experiment. According to Einstein's thought experiment, before firing the electron, the first slit had to be completely stationary without any tiny movements. Accurate experiments were possible only if the exact position of the first slit was known, and it had to be perfectly stationary to not affect the experiment. But according to the principle of uncertainty, it was impossible to know the position and momentum at the same time. However, to conduct Einstein's thought experiment, a perfectly stationary slit was needed. This meant that both the position and momentum of the first slit were known. In the end, the premise of Einstein's thought experiment was violating the principle of uncertainty from the beginning. Einstein, who was eager to bring down quantum mechanics, was thoroughly defeated by Bohr's unexpected defense, and the 5th Solvay conference ended in Bohr's victory. However, even so, Einstein could not accept quantum mechanics. Eventually failing to bring down quantum mechanics, Einstein sharpened his sword for the next conference. And 3 years later, at the 6th Solvay conference, Einstein brought a more refined thought experiment to completely bring down quantum mechanics. This thought experiment made Bohr speechless like a dumbfounded person, and quantum mechanics faced its greatest crisis since its inception. Next, we will explore the crisis of quantum mechanics. In the next episode of Room Science, this has been Room Science.